Hi, 3.1a. I'd like you to make this graph. Just make a y and x axis. Go out to 3, 1, 2, 3. And then go out to -3, 1, 2, -3. Just go up 1, down 1. And you're going to put a little dot here at 2, -1. And then put another point here at -2, 1. All right, and the best way to graph this, start from the origin and just go down to 1 and up and put an arrow. It's going on to infinity. And then start at this origin right here, go around and go down to -3 and then put an arrow. It's going to -infinity. Okay. Now this black graph we know as f of x, so I titled it f of x. Now even though this goes up to infinity, because this is the second highest point that we can see other than this line going up, we call this point right here, it's like a vertex, you can think of it that way, as a relative maximum point. And the same thing over here, you can think of it like a little vertex. We call this a relative minimum point. So relative min. Okay, now we're going to look at where f of x is increasing and decreasing. Okay, and we're going to use our interval notation. So I'm going to state f is increasing on. So we look at the intervals, it's increasing. Well, we know from here to here it's increasing. And that is, out here is -infinity. So from -infinity to -2, remember interval notation. This means from this right here are x values. So on our domain from -2 to -infinity, f of x is increasing. So we say f is increasing on -infinity to -2. And we can see it's increasing right here. Right here it's increasing. And this is from 2, let's say I'm going to put that to infinity. From 2 to infinity, it's increasing as well. So from 2 to infinity. All right. So where is it decreasing? F is decreasing on. And that is right here from -2 to 2, you can see it's decreasing on -2 to 2. All right. Now notice something. Here we have x as -2, f prime of -2. Right here, if we took the derivative right here, the tangent line, slope of the tangent line would be 0. So f prime of -2 is 0. Do you see that anywhere else? Yes, that's right, here as well. This is at 2. F prime of 2 also equals 0 because the slope of that tangent line is 0. Okay, we say -2 and 2 are critical values. And we're going to use this a lot, critical values. This term. We say -2 and 2 are critical values. Okay. All right. We're going to look at a theorem now. So I'm going to erase this. I'm going to draw this picture right here. Okay, I'm going to say this is like point A, and this is point C right here. So these are x values, A, C, and B. That's not A, this is A. Okay, so what about f of A? There's f of A. Now f prime of a, f prime of a, is this increasing right here? Can you see that if I made a line, I'm going to put it in blue. If I look at this tangent line at this point, it's kind of a funky tangent line. All right, so imagine that tangent line at that point. We can see that this particular slope is going to be positive. So we're going to write it's greater than 0. So the derivative, which is the slope of this tangent line, is greater than 0. Okay? So now here we have c. This is f of c. What can we say about f prime of c? That's right, f prime of c, because the slope is 0. So I'm just going to draw a tangent line to c, equals 0. Okay. Now how about b? If this is b, this is f of b. And if we were to draw a tangent line there, we can see that it is decreasing and it's negative. And so we can say f prime of b is less than 0 because the slope's going to be negative. Okay? All right. So here's the theorem. It's called the first derivative test for relative extrema theorem. And we call it the first derivative test for relative extrema. Okay, and it states for any, I'm going to underline any, continuous function f that has exactly one critical value c in interval AB, okay, so let's start with what this states. For any continuous function, this is continuous, f, that has exactly one critical value, f prime of c equals 0, value c in the interval AB. So from here's our A to B, c is in that interval. And so it's stating for any continuous function f that has exactly one critical value c in interval AB, then it has three things that go along with that statement. F has a relative, I'm going to just, relative max. F has a relative max at c if f prime of x is greater than 0 on AC, and f prime of x is less than 0 on CB. So go ahead and write that down and we'll look and see what that means. Okay. F has a relative max at C if f prime of x is greater than 0 on AC and f prime of x is less than 0 on CB. Okay, so this is AC right here. This is the interval AC. F has a relative max at C if f prime of x is greater than 0 on AC. So you can think of it like this. You can think of f prime of x, we know is greater than 0, right? Because we stated it right here, and this would be the same thing here. Okay, so any point x between A and C, if it's f prime of x is greater than 0, then f has a relative max at C. Okay, and then it states, it says so it has to go the other way now. Here, f prime of x, must be less than 0. All right, so it's saying basically, if you have a slope here that is positive, and you have a slope here that is negative, then of course there's going to have to be a relative max. That's all that really says. Okay, let's go on to F has a relative min at C if f prime of x is less than 0 on AC, on the interval AC, and f prime of x is greater than 0 on CB. So that would be going the other way if we were like this. Okay, then it would be saying this one's less than 0, the slope is, this one's greater than 0, therefore we're going to have a relative min at that point. All right, and then we have one more, 1, 2, and now we're going to put 3, the third part of this theorem. Okay, number 3. F has neither a relative max or relative min if f prime of x has the same sign on AC, on the interval AC, as the interval CB. And that makes sense. If the slope is the same, like they're both positive, then we're not going to have a relative max or a relative min if they're both positive or both negative.